So K'96 reflects who we are as a batch as well. And why are we doing this TED K'96 in this particular form? TED essentially stands for, originally, it was meant for technology, entertainment, and design. It was a format in which people in the technology, entertainment, and design can come together to share ideas and debate and discuss. Now, all our age-old philosophies worldwide in any culture were all developed by people interacting with one another, challenging each other, and debating it. So, but since we started growing,
virus, retrovirus, biovirus, bacteria.
that you mute, please.
Same page, same slide.
Can you mute yourself? Right. So since it moved beyond just the technology, entertainment, and design, it moved into psychology, it moved into physiology, it moved into medicine, it moved into healthcare. So hence now TED just remains as a platform of knowledge sharing. That's what it becomes. To me personally, last year, when we all met for the 30 years of knowing each other, one of the themes that we picked up was, we said that everybody is a hero in our own life. And we would have achieved what we are achieving as per our milestones in our life, and hence we are all heroes, is what we said. So what we would want to understand in this forum is to know each other a little more. And it is also an opportunity for people to showcase and people to tell what is their side of story. So because beyond this 30 years that we have known each other, there are also a lot of stories that people have encountered, a lot of events that has happened in people's life, which are extremely inspirational, and it could really be helpful for us to know each other. And if you have something that you really do for a living, which you think is very interesting for other people to know, please come and share. And if you're very passionate about something and you want to share that, this is a platform for you to share. And more importantly, it's about us. It's about us. It's about us to know each other a little more and know each other in terms of who we have become and knowing each other a little better. That's the idea of TED 96, K'96, right? K essentially stands for K2, 96 stands for the year that we passed out. What can you expect? So you can expect one of our own batchmate who comes in and says about who he has become, what he is currently doing. And it is also a platform of appreciation for learning and understanding the achievement that that person has made and become. And it is also a platform for us to understand and learn something new, and nothing like listening to your own friend. So because these are people who have been our roommates, these are people who have sat next to each other while we had lunches and dinners. And these are people with whom we have had stories in our life of 4 years that we have been carrying here, right? And beyond everything else, it's also the time for us to come together. So hence, that's the forum that we are trying to create here. And how are we doing it? It's simple. We are targeting anywhere between 6 to 9 TEDs per year, which essentially means once in 2 years, or in certain occasions, we may do more frequently, is what we're trying to do. And we would reach out to the speakers, and we'll also identify what areas they are very comfortable to talk to and what areas they're comfortable to talk to our own friends. So what I know need not be something that I want to talk in this kind of a forum, right? That is something that we will do. And we have set up an organizing committee, which would help every speaker to be able to prepare well and present themselves very, very well. So there's a speaker support forum that is also there. And speaker support forum now, இது இங்கிலீஷ்ல மட்டும் இருக்கணும் நெசசிட்டி கிடையாது. இங்கிலீஷ்ல இருக்கலாம், தமிழ்ல இருக்கலாம், as long as parliamentary language இருந்ததுன்னா இருக்கலாம், ஒன்றும் பிரச்சனையே கிடையாது. And it's also a communication forum. So we communicate to people regularly on who is speaking, what are they speaking. And we also seek, if you want to come and say something, you want to talk something for a smaller period, 10 minutes, 10 minutes time, we'll arrange that too. So it will usually be a virtual format on Zoom, and it will range anywhere between 30 to 40 minutes, 45 minutes for the speaker and 15 minutes for the Q&A session. That's the format in which it will go. And one suggestion, thanks to Siva, whenever possible, if you can get together as teams sitting next to each other and going through this together, that will be a great opportunity. So please make yourself comfortable to meet with people who live around you in your locality. And then lastly, so who are the people who are going to be here? the most important thing is anybody who has got an idea, who wants to talk, can come and speak. So, and the only criteria that we would choose is it needs to be fit for consumption of your family, which means you along with your children can sit, you along with your spouse and children can sit and watch and listen to. So essentially, it will have to be very civilized. It will have to be parliamentary only, and no crude jokes or no double entendre kind of things is not entertained. But if you have a good informational knowledge that you want to share, something that's educational, entertaining, yes, we would welcome. Your humor is always welcome as long as it is sensible, right? And one recommendation that you have is do something original. So we don't have to do something because we need to do something. So as long as you have something that's original that you want to talk about, please come and talk something that's original and it's real. And we would not have a censor. Okay, so this censorship is something that we will not do. We would expect the speakers to be self-regulated. They should know what is right and what is not right. So, and if you have any doubts, we as organizing committee, we would help you to understand what is a good thing to do and what is not a good thing to do. So the organizing committee would be responsible for identifying speakers, helping them with content, and also helping them to be able to present the content very, very well. And last but not the least, the continuous communication that we need to do to ensure that our forum is continuously getting engaged. So that's all from my end at the starting stage. So now I'm going to pass on, and any comments, any information that you want to share, please feel free to put it on the chat. And if you want to show your appreciation, there is always emoticons that are available for you to show clap. And if you have a question that you want to put in, please mention, please type it in. So we will be tracking what is it that you guys are talking, and so that we'll be able to build the conversation very, very well. So may I know James to formally invite our guest speaker, guest of honor of the day, Ramesh. Ramesh, you can smile. Please smile. James?
Yes.
Okay.
Yeah. Welcome, Ramesh. I'll put Ramesh in spotlight. Yeah. Welcome, Ramesh. Very, very happy to welcome you. I remember like 31 years ago, 1992, I welcomed you into a room number 141. Now 31 years gone. So I'm very, very happy to welcome you as our speaker for this event. First event, and very happy to welcome you. It's not only welcome speech here, so I'm going to give you a little bit introduction to Ramesh. We all know Ramesh very well, a very, very known person and very calm and quiet and a very happy-going person. But now he's a scientist working in Germany for the last 12, 13 years now, Ramesh, right?
Yes, James, that's right. Yes.
Yeah, 13 years now. So Ramesh, after finishing his cornea life, started with the IIT Bangalore as a project associate, and then moved to Raman Research Institute, Bangalore, worked there for 4 years. Later, Ramesh moved to Netherlands to work as a software engineer, and then took up a PhD course, completed his PhD at Amsterdam University 2009. And then moved to Germany to work as a research associate, then later joined as a scientist. Now for the last 12 years, Ramesh is working as a scientist, as a radio astronomy scientist. Other than radio astronomy, Ramesh is a very, very keen cyclist and runner. Completed his half marathon recently. And married in 2008 to Priya, and blessed with 2 kids, 1 boy and 1 daughter. So yeah, very happy. Ramesh, welcome to our event, and we are all very, very excited to hear from you.
Thank you, James. Thanks a lot for that warm welcome. Okay.
It's a pleasure to welcome you formally. And I think it's also important for us to welcome all our guests who have attended, who have come and logged in today. Guys, thank you so much for showing this support. I think this talks a lot about who we are as a batch and how we support each other's idea. So being the first event, so we really look forward for your participation, and feel free to give us a comment and any feedback that you might have. We are always listening. And please put in your questions, whatever you might have in the chat as well. So Ramesh, so without much ado, let's start into getting you to talk about your journey and your experience, right? So what I've done,
Okay.
yeah, you have anything to
Yeah.
add?
No, I'll just go on. So I thought you're handing it over to me. So
Right. So what I've done is I have essentially put up a small presentation.
Okay. Then you know how when you prepare the batter usually at night, in the morning it becomes.
Okay, Ramesh, can you see?
yes.
Can you see the screen? I mean, so
I'm on the spotlight, so I see this myself.
right. Okay.
Okay.
So we have captioned this particular discussion with you as Rising to Stars with Ramesh. It's how we have captured, right? So we all know that you have been working with neutron stars, and we know that there is a lot of chat that has happened on black holes and whatever we understand of black holes, and a lot of debate did happen. But fundamentally, Ramesh, what we know of you was you did a 4-year engineering course with us, wherein you did electronics and communications engineering. And how did this transition even happen into astronomy? Just walk us through that path, Ramesh.
Okay. Okay, so to start with, let me just first, thank the organizers like, Balaji, James, and people who are behind the scenes, are organizing this event. I think it's a great initiative, and I think this is a wonderful way of getting together, and I think it's a useful way to spend your time, even if it's just 1 hour. Therefore, I'm just really looking forward to sharing some of these things that I have, at least in my field, the passion or the excitement that I experience. So that is really the very first bit that I wanted to say. And secondly, Balaji, I actually worked on a small presentation that actually walks through some of these things. I actually based the presentation on the set of questions that we had, and especially with the responses that the people gave on the Google Docs. So I used that to create a small presentation. I don't know if you want to walk through that, or do we, get into the order that you're suggesting. You ask something, I answer something, and go on in that fashion.
So the purpose of doing this, Ramesh, is actually to understand your journey and ask you the questions that probably we have. You know what questions people have asked and what questions people have voted to listen from you, right? If you're present, you think is the best way to do it? I mean, so we would love it. I mean, please go ahead. Please go ahead.
Okay. So let me then, just maybe run through the presentation a bit. And then, I tried to summarize all of your questions in there. And then I think we will eventually get to whatever you asked over there. And if there's anything that looked very vague, or that does look like, it needs more details or explanation, I think I'm happy to address that in the end. But maybe let me just rush through the presentation, and then we can get to some of these burning questions.
Sure. The only liberty that I will take, Ramesh, here is, so if I think that could be an area in which we should spend a little more time, talk about it, give me that liberty to stop you and something to you. Is that okay with you?
Okay. So let me get through some of this presentation, and then basically it's like a talk that we do in our field. In fact, I never done a talk for popular audience. I mean, I wouldn't call you popular audience, but kind of to an audience of this type, kind of pitching the material to an audience of this type, because I think in the business of research, you'll also have to be able to communicate the results. And that was a very hard balance that I had to.
Ramesh, 1 second. You may
Yes.
need to adjust your mic. Is it
Don't you hear me well?
I think few people are not hearing well, so you can
Okay, give
adjust.
me a sec. Let me try to
Muffled.
play around with
It's
my
very close
settings.
to your mouth.
Yeah, just lower it down.
Muffled.
Hold on, I'll have to choose a different mic. Is
It's
that
good. It's good for me, but
It's good.
Is that better?
yeah, better.
Okay, cool. Okay, no, I avoided using this one because it echoes my voice and I feel very uncomfortable with it. But no problem. Let's go around with this one. So yeah, so as I said, it was a bit hard to prepare this material because some of these things are completely out of my expertise, and therefore I just try to do the best guess at it, and let's see how far it goes. And then if it gets too complicated, Balaji, you just say, okay, please shut up, and I'll stop there, and or I'll keep going if there's no response. All right, okay, let me start with my screen share. So do you guys see that? Do you guys see that?
You're on mute.
Yes, sir.
Okay,
Yes.
good. Okay, so here we go, guys. So what I tried to do summarize here was like try and just club these questions that you had and then provide some answers, at least to some areas that I have a bit of knowledge, and yeah, and then see where this goes. So as instead of just going through, chugging through the list of questions that you had, I think it will be much more, productive if I provide some background and then base the questions off that background, because that I think is probably much more effective. And as I said, I'll only give some answers because I'm not an expert in all of the questions that was posted. And then finally, we can again go through a round of questions and try and clarify some things that wasn't clear over here. So here's the list. So this is basically the responses that Balaji collected over Google Docs. I just tried to rearrange in the order in which it was posted. So which kind of said like the questions that received the most votes. Of that, the very first one was the recent discoveries in my field. So that amazed me, and kind of challenges in neutron stars or black hole studies, the Big Bang Theory, the expansion of the universe, and some real life applications. So I just collected these as the topmost things, and these will form the background of the material that I'm going to give soon. And then I also try to address a bit on career in astronomy and astrophysics, some suggestions and so on. And then finally, there are two questions which I'm really not an expert, and I think some of you know much better than me. And whatever I have to do, I really cannot do justice to these questions. So I'm just completely leaving them out. And yeah, so that's where we are. And here we go. So I'll just move this. Sorry, there's this ugly Zoom bar. Okay, so yeah, so before we start, one thing that is a start of everything is the Big Bang, as we know, the universe as we know now, at least what science says. So that is what I'm going to say, because I cannot make any other judgment. So this is what it is. So the observations back in 1965, these were two engineers who were working for Bell Laboratories. So what they did was they were trying to build a receiver for Bell Labs. They were trying to see balloon experiments, trying to detect radiation from them. So they built this, horn antenna. Do you guys see my cursor over here? Yeah, okay. So I can use this cursor as the pointer. So they built this this horn antenna way back in 1965. And then since they were detecting very weakly scattered radiations that are coming off the balloon, they wanted to, get this receiver as sensitive as possible. So therefore, they built a very sensitive receiver. That explains the huge horn over there. It needed a huge collecting area. And then, they also cryogenically cooled the receiver. So the thermal noise had to be reduced. So they used liquid helium and cooled it down to 4 kelvins. So, but despite all of this, they always found that they never achieved this designed temperature of the receiver. So, or the thermal noise background of the receiver. They always found some excess, and this excess was, as they measured, 3.4 kelvins. So this was perplexing because they tried to observe in different directions of the sky, different times of the day and night, and so on. They carefully removed all radio interference, and still they found this uniform excess noise wherever they looked at. And this excess noise is showed here in the image on the left bottom. So this excess noise is currently measured to very, very accurate levels. It's like 2.7 kelvins of excess noise with only a millikelvin of variation, as we see over there. So you see this very uniform background devoid of any features almost, because there's no structure or anything. And this is the whole sky as we see it. And of course, this isn't very easy to get. You'll have to remove the galactic foreground. The image on the top shows the same image, but with the galactic foreground. So you see the galactic center, you see Centaurus A and Large Magellanic Cloud, Orion, all of these other sources which are in the foreground, and also the galactic disk. So all of this has to be removed carefully, carefully the data be cleaned, and then you get this background. And this right now we know it is 2.7 kelvins, and this is called the cosmic microwave background now. And this is one of the key evidences for the Big Bang. And let's come to that now, if this works. Yeah. So why was the need for such a Big Bang, basically? Because by 1950s, people had already developed theoretical models which are based on general relativity. And general relativity was by then, very well tested, almost, because it really explains some of those discrepancies people measured in the solar system. For instance, the way the Mercury precesses. So all of these were beautifully captured by general relativity, and it very soon was a theory which was superseding Newton's theory in terms of the predictive power. So, so obviously, it meant that theory has some universality and it applies to the whole universe. And they try to develop models of the universe then. And by this point, in 1922, already we knew that the universe was expanding because people observed galaxies in different directions of the sky, and they all seem to be receding from us. So wherever you look in the sky, there are galaxies very far away, and they seem to be all moving away from us. This kind of already indicated that the universe was expanding, and there was no theory that was explaining why the universe has to expand. And another key observation was there was also, lots of helium, hydrogen, and lithium all over the universe. And these are elements that we know how to detect them. So, at this point, it was already very clear we need something like something to explain the observed features of the universe. So then around 1900, there was a person called Max Planck. He was here in Germany, in Berlin. He was studying a completely different thing. He was studying, how to assign temperature to a glowing body. For instance, when you heat a piece of iron, it glows, and then how do you assign a temperature to it? And this was all in the time when electric bulbs were found, when tungsten was glowing. They wanted to find out what the temperature of it, and so on and so forth. And he kind of is the father of what we call as quantum mechanics now. And then he kind of came up with this law which tells the intensity of the radiation given the frequency, and then it tells how this radiation is quantized for a given temperature. So using this relationship, you can, based on the wavelength of the radiation that you observe, you can assign a temperature, wavelength, or frequency. Both, you can use them interchangeably. So this equation, you can just forget it now. It's only to tell you that some of these observations that we make can be assigned to a model. And that is what happens to this cosmic microwave background. And if you observe at different frequencies, the curve here on the right tells how the intensity of this frequency varies. So you see, some things that are going from just under a gigahertz down up to 800 gigahertz. So some of these points later on in squares were taken with a satellite called the Planck satellite, and that produced excellent data, that went all the way from 80 megahertz to 80 gigahertz to 800 gigahertz. So all of this data, fits such a curve that is shown in the that's shown here on the left, almost beautifully. And then this fit, if you assign it to a temperature of a black body, it's exactly at 2.7 kelvins. So what this means is, this radiation over here that's observed over different frequencies, if you fit a curve to it and find out what this curve explains, it just fits this model so beautifully. And this kind of shows there's a radiation that's at 2.7 kelvins. There's a black body that's at 2.7 kelvins. So this is the cosmic microwave background. It's called microwave because it peaks in microwave frequencies, and that's at 2.7 kelvins, as we know now. Another key piece, so this is just what I said earlier, like, if there's a glowing piece of iron, you can, based on the wavelength that you see, the yellow over here, you can kind of tell what temperature that is. And the same thing can be applied to, for instance, for a sun, if you want to know what the surface of the sun is. In this case, the curve that is overlaid on the data over here is at exactly 5,778 Kelvin, which is, here we call it a black body that's radiating at this temperature. And if you try to find out the intensity of wavelengths that are being received on Earth, and this is how it fits the data. So this is, what we say, an excellent fit to the model. So this kind of, tells the universality of such a physical law that was, found somewhere, someone sitting in Berlin, and that seems to have such a wide applicability. This is the beauty of physics, that whatever you derive here, whatever you study here, seems to have a much wider applicability to almost, over the whole universe. And the next key thing that kind of, also said, that also, kind of burning to have this concept called Big Bang is the chemical composition of early stars. Most of them seem to have helium and hydrogen, and also that the old galaxies look very different. So we'll come to that in a bit. So if you put all of these things together, this is what, if you kind of put these things together and try to build a picture, this is what seems to have happened. So there was a point 13.7 billion years back, when all of the matter that we see, when all of everything that we see was compressed into a point, and that seemed to have exploded. And the very first after the very first expansion is what you see. This is the radiation that we see as cosmic microwave background. And for about 400 million years, nothing seems to have happened. And after that, the very first, stars and very first galaxies seem to have formed. So this point, after a few milliseconds down to 400 million years, is called the epoch of reionization. And this is where in the lighter elements were formed, basically like hydrogen, helium, and lithium, and so on. So these were the very first elements that formed, and that kind of tells why we see helium, lithium, and hydrogen all over the universe, wherever we measure. And that also kind of explains why we see this radiation, which is like, uniformly seen all over the sky. And this expansion also tells like why these galaxies over here and this edge are receding from us at very great rates. So this is the reason why we think there was a Big Bang, because this is the best observational model that we have, or best observation that we seem to have, and fits an hypothesis called the Big Bang. So it is the same picture that we saw earlier, but it's like, kind of turned around. And here the Big Bang is shown here in yellow on the or white actually. And then when the soup or the plasma starts collapsing, it all turns red. And then at some point it formed into this very proto galaxies. And what's shown over here is the Hubble radio telescope, for instance. And this one, with the Hubble radio telescope, you see newer galaxies that are younger, and then you can also see the very ancient galaxies which are like further back in time. And this kind of shows that the old galaxies that were discovered that were not discovered, studied in infrared, looked very different from these galaxies which are seen in normal light, so which are in the foreground. So these two, population of galaxies looks very different. So, whatever we see, this kind of the Big Bang also fits this data very well. Now, with these observations, you can also, get redshift of galaxies. Redshift of galaxies is when when you detect the light from a from this galaxy which is receding from us, the wavelength gets redshifted or increased in wavelength and decreased in frequency. So it looks redder. That's why it's called redshift. And these optical observations also show the redshift of galaxies. Basically, it tells like the further the galaxy is, the faster it's moving away from us. And this seems to move away from us in all directions. So this particular image shows so-called a Hubble deep field. So this is apparently a blank patch of sky as seen from Earth, and this is like really a tiny patch of sky. It's 1/10 the size of the moon. And in this deep field, Hubble's deep field, you see, tons and many galaxies, in all forms, in all orientations, and so on, and also in different stages of evolution. The redder the galaxy, the further it is, and the less evolved it is. And the galaxy that has more structure is more in the foreground and is much more evolved. So here we are seeing, like, basically a history of the universe in this deep field. Now, how do we measure these things called redshift? Because we seem to, much of our results seem to impinge on this in this concept called redshift. How is this measured? For instance, here's a cartoon of a galaxy here on top right. It's basically a drawing. It's not a real picture. But what it shows is, all elements of a galaxy. It shows a spiral galaxy, and it shows the radio jets, and there's possibly a central black hole. Forget the labeling over here. It's all in French, but there's a black hole. That's the trou noir. And what this shows is, like, this is what you would observe it as in a a typical 1 meter telescope or something, optical telescope. And once you have such an observation, you can put in a slit, and then through the slit you can do something called spectroscopy, and this is what you will see as the image on the top right. So once you remove the background and calibrate the data, you can arrive at a graph that is shown in red over here. So with this graph, you can also assign the different peaks to different elements that we observe. So how do we know that these are the different elements? We know that these are the different elements because we can do these experiments here in lab, and we can use quantum mechanics and predict exactly what the frequencies that we should be seeing. And so this is the beauty of the theory that I was saying. Something you work out here in lab, and you predict a frequency of emission, and you see that exactly on the sky, and then this kind of tells exactly what we are seeing. So what we see here is the peak over here is H alpha, or the neutral hydrogen, and then it shows a distinct peak. Now, because of redshift, when it's moving away, this will look more redder, so it'll look the wavelength will reduce. So that kind of tells us what the speed at which it's receding, and the width will tell you about something about the galaxy and how it's rotating, and so on and so forth. And by this you can study the element abundances, and then different stages of evolution. For instance, you see H alpha, H beta, H gamma, which is all different stages of evolution of the galaxy. So this tells something about redshift. It tells the composition of old galaxies. So all of these things would come together if you have this concept called Big Bang. So that's basically why we think there was a Big Bang. So now we spoke about the universe as as though it's a background or as a garden. But now you'll have to come back to our home now. So this is the universe as we know now, and this is the galaxy in the foreground. And in the galaxy in the foreground, we are in a much even closer space. It's basically our living room. In this living room is what we call as what you would call the local group. See, the local group has the Milky Way, the Andromeda Galaxy, and the Triangulum, and so on. And our galaxy is, such a spiral galaxy, and the sun's orbit around the galaxy is shown by this yellow circle over here, which takes about 270 million years to finish, thereabouts. And from a galaxy, these are the directions of the Andromeda and Triangulum galaxy, and other members of our local group. So to put things in context, here's the thing. So here's the Milky Way, and here's where here's where we are. Basically, this is our living room, as I said, and this will be the sofa in which we are sitting. So in that, we are, of course, in the solar system, and in the solar system where is our home, and the solar system is also home to the nearest star that we know, the sun, and here's how a star exists, basically. So a star is it exists because of nuclear fusion. As we know, helium and hydrogen are the most abundant materials, and so is most abundant elements, and so is a star. It's basically a ball of hydrogen and helium. And what happens is nuclear fusion. Basically, light elements like hydrogen combine to provide deuterium, combine to provide to make deuterium and another hydrogen atom. In the meantime, a small fraction of the mass is converted to energy, and that's what is shown as gamma rays escaping from that from this reaction. And this thing successively happens, and you combine deuterium and hydrogen to form helium. You produce energy, and then so on. You produce heavier and heavier elements. This is nuclear synthesis. That's nuclear synthesis and fusion that's happening at the center of a star. And this energy that is being created is what creates this pressure, the radiation pressure that's pushing the star outside. At the same time, the star is so massive that the gravity is trying to compress it and crush it. And then when these two things balance, then you have this happy medium where the two forces balance, and then you have the star glowing for several billion years. Now, this one cannot happen forever because, as I said, there's nuclear fusion that's happening at the center of the star, and then the lighter elements come in to provide heavy elements, and you get to a stadium where you stage where you combine silicon and silicon, and you produce iron. So the iron, this nuclear fusion reaction is unfortunately endothermic. So when it's endothermic, what happens is that it no longer produces radiation pressure, and therefore the star, which was burning for several billions of years, suddenly sees itself without a force to sustain, to protect itself against the crushing force of gravity. And then when this happens, that's when a star explodes in supernova. So what's shown over here on the right is the Crab Nebula, or a star that went supernova some 1,000 years back. And when this explodes, then you'd see that the star sheds the outer layers, and then it has two possibilities: either become a black hole or a neutron star. In this, what I'm interested in is something called neutron star. By the way, the one that such a supernova is called electron capture supernova, and that's what the small equation above shows. Like you have a proton, and then it captures the electron, and then what happens is the electrons get so close to the protons, and they annihilate, and they produce copious amounts of neutrino, and this is what powers the supernova in the end. So once that happens, when things are right, when the conditions are right, when the core is, between a few solar masses, like, up to 3 solar masses, then the core collapses to form something called neutron star. So in this case, as I said earlier, the protons and electrons get too close, and they annihilate, and they produce neutrinos. And what is left over is just neutrons. And since neutrons have no charge, you can pack them much more densely, and that is what happens. So imagine something that is several times the size of the sun, or the mass of the sun. In this case, we are talking about just 1.4 times, because we are talking just about the core. And this is, by the way, called Chandrasekhar's limit. And when the core exceeds this limit, that's when you have a neutron star. And since the neutrons have no charge, they can be compressed greatly, and then you have, in the end, you are left with a sphere that's only 20 kilometers wide. And the star that was so huge, it gets compressed to a tiny ball now. And the magnetic field that was present in the star gets compressed as well, and then that kind of boosts it to very high levels, about 10 to the 12 Gauss. This is what is it? It's like 1,000 or 1 trillion Gauss, and compare it to a sun, which is just 1 Gauss. So that is the amount of magnification and magnetic field that you get. And then because of the formation scenario, the way because you have to conserve momentum, the star collapses. It's like an ice skater who's like spinning on ice rig like this, and when she draws her hand close together, she starts spinning faster and faster. So the same thing happens over here. The star starts spinning so fast that it can spin up to 43,000 times a minute. And as I said, in the formation process, the rotation and magnetic axis are misaligned, and because of which then you see all of these observational things that you see on Earth. And this produces the pulsed electromagnetic waves along the poles, along the magnetic poles. And as I just said earlier, it is the endpoint of evolution of a star. And this animation shows how this, the emission is produced and it's received on Earth, or it basically tells, what when a neutron star becomes a pulsar as it's observed here on Earth. So the yellow cones over here are the areas where the electromagnetic emission is produced. And as the star spins, and when this radio beam sweeps our line of sight is when we receive a pulse here on Earth. And you can, if you have a radio telescope and you observe it, you get a pulse every time it spins. And yeah, this is what we observe. And for instance, this animation here shows that you get a pulse every time this sweeping beam passes our line of sight. But when you average as a few hundreds of them, you get a very stable emission profile as here in the right, and with which you can do all of the science that we are talking about the mass of the neutron star and about the how it's formed and so on and so forth. Of these, what is more interesting is when neutron stars are in binary, as we show here. It's like like Earth is Earth and Sun are a binary in some sense. The Earth and Sun go around something called the solar system barycenter. So something similarly over here, these two stars are going through a center of orbiting a center of gravity, a point called the center of gravity. And what's more interesting is like when the emission from one star goes through the potential well or the gravitational well of the other star, then it is probing actually the space-time curvature as we see over here. So how is it observed here on Earth? In Earth, when at different orbital phases of the star, the signal seems to arrive later and later. So that's what this curve shows. So this one is a very important ingredient. And if you use general theory of relativity with this curve and with a few physics, you can tell something about the mass of the stars and the magnetic field and a whole lot of things. So of course, since these are very, very weak signals, then you end up using some of these big telescopes, like the one here on the top left. It is not quite a big telescope anymore. It's 100-meter in diameter. It's something like 4 football fields over here. So this is the scale of observational facilities that you need on Earth to study these systems. Okay, now I think I've provided some background. So what do we do? I think I've collected this list again, just to to remind you of what it is, and then I'll go through the list now. And I think I can go through pretty quickly, and then maybe take questions. Or do you want to do a different way, Balaji?
Yeah. So let me quickly take a moment there. I mean,
yeah.
Thank you for having to condense huge amount of knowledge into such a small capsule and feeding that to us. So because you've gone from the hypothesis of how Big Bang theory is a possibility and scientific research on that, and from there you went all the way down to talk about what happens to a star and what happens, how does a neutron star come to being. That's an amazing journey that you walked us through. I think there are some very interesting technical questions that's coming in. Pushpavali, I specifically asked you for one. But before that, Ramesh, I think we would like to spend a few minutes to understand your journey or transition between electronics and communication to astronomy and astrophysics. How did that happen? Tell us that story to us, please.
Okay, I'll try. I think I put in a slide, but it probably wouldn't say much. I think. Let me see if there was. Okay, I think I just put in this slide because anyway, first of all, I wasn't very comfortable in talking about myself. I don't know why, but let me try to do the justice to this question, right? So, I think to start with, right from my youth, I think I was mildly nerdy, as like most of us, I think. So I was like ripping apart motors and cassette recorders, and I was always interested in things that moved. I still remember reading a Tamil book that said talked about how a radio works. It was from Om Padipagam way back then. So it was like a very interesting, a childhood in that sense, because I did not have much friends, and I spent lots of time with books, of reading all sorts of books. By the way, I wouldn't say this was the only book I read. So books that were appropriate for my age, inappropriate for my age, everything was done. But lucky thing was there was no TV, so you had to spend some time reading. So that was the good thing. I wouldn't say that I was like I was also awfully interested in the way the universe worked, or had a wonder of what the sky is, or anything of that sort. It was only a passing interest. I mean, okay, living in Kotagiri, it was like you had good nights, clear nights, and then it was some nights were very clear, and you kind of wondered, okay, what this was, and that was it. And that was just a passing interest. And what might have been interesting was, I think, the subject called EMWG that we had in the 5th semester, that kind of brought some interest in this kind of theoretical approach to things, like something that people way back in 1850s derive, and then they can tell something about the speed of light. All that was fascinating for me. Basically, I'm talking about Maxwell's equations, and how people arrive at something at the speed of light way back in 1850s, when there was nothing around to measure that. So that was, it all stayed in the realm of intrigue at that point, I think. And also, what happened towards the end of last semester was that we did, Arunachalam, Paramassivam, Chinna, and Andrew. We all did a project with Smiles, and I think that was very useful. And then afterwards, it was completely coincidence the way I got into Raman Research Institute, because I just responded to an advertisement in newspaper, and I happened to be be invited for the interview, and I explained about. I had to explain about my project. Of course, it was completely wrong, but the interview panel seemed to have been convinced that I was probably capable of doing something useful. So they gave me a job in Raman Institute, and I was offered the job of a receiver engineer over there. So I was supposed to take care of receivers, and at that time, what was really interesting was signal processing, which we did not have in a syllabus at that point, but also the idea that somehow you can manipulate numbers and mimic what happens something physically was was very, very thought-provoking for me. And so I think I went into a little bit into instrument development at that point, where I developed my very first spectrometer. So at that point, I think something happened. I kind of thought, okay, I'm developing all of these instruments, and you have these astronomers who come by and say, okay, yeah, I measure Mesa, I measure that galaxy, I see this cloud moving at that frequency, and so on. And that kind of, it just raised my curiosity levels. And it was at that point I kind of decided, more or less to get into astronomy. And when I got to Netherlands, again, I came as a software engineer. And one of the first things that I kind of, bargained with my employers over there was that they allow me to do a PhD. And that's how I really got into the field, because in the end, I think I liked the field at that point, and even now, maybe. The only way to survive in the field, I thought, was to have a PhD, and I just went by how would I say, my gut feeling, and then did a PhD, which was a bit of a difficult journey coming from electronics background and trying to catch up all sorts of literature, but. Yeah, it seemed to have worked, and somehow my current employer also thought, I was a good enough guy to give a permanent job, which is very difficult in this field. And I seem to have gotten the job, and I stayed on. And yeah, I think that's how I'd kind of summarize the way I got into the field.
I think everybody would agree to this, because you sounded extremely modest, but then behind that modesty, we could see there is an application of mind that has happened. There is openness to learn that has happened. And the words that you used in terms of curiosity and inquisitiveness, I think those would have surely mattered. And I think the way you spoke about yourself is also that you've been at the right time, at the right place with the right people, right? So
yes.
any of these things do not happen by default. There is some amount of conscious effort that is not an effort that's put in. So thank you so much for saying this. Now, just staying on that note, Ramesh. Now, yeah, so we read about this, we talk about redshift, because that's another question that's come from one of the child of our classmate. I mean, so where the child is asking, so now once this redshift has happened, now do all these planets which are in the redshift, do they again go back to a black hole? Is a question that's being asked. Is it something that you would be able to answer?
No, I wouldn't say it'll go into the black hole. So so the current theory, current observation points that there was a big bang and the universe is expanding, and whatever I showed as distant galaxies have lots of stars and lots of planets. Just take our own galaxy, we have 1 billion plus stars. So do all of these stars, do they go back to the central black hole? No, they are just going around. So a black hole is also such a tiny object. It is, as we say, it's a singularity in space-time. So which means like a neutron star is the next best physical thing that we have, which is only 20 kilometers wide. And even the galaxy is so big. What is the probability of we passing a neutron star in our journey around the galaxy? It is tiny because because the space is mostly empty. So the time that the probability that you go across a neutron star is so low. So the only way I can only tell that whatever that is such a tiny chance that we go back into a black hole. Even in our case, I think we'll be just perhaps the universe will go colder and colder and colder. I mean, we are talking about several billions years from now,
right,
when humans are probably long past and gone. So we are never going to go into black hole. I think that I can tell to the best of my knowledge.
And an associated question with that is now we are saying that the galaxies are expanding and then they're moving. They're forced to move away, right? So
the universe is expanding, yes.
Yeah. So does that mean the stars and the planets, do the distance between them currently what it is also would change because of the expansion?
Well, I mean, what we know is the galaxies are expanding. I mean, but we know that within our galaxy we are not flying apart. We are being held together by the local gravitational potential. Right. So we have a supermassive black hole at the center of a galaxy, and that almost all galaxies have such a massive black hole at the center. Which seems to have formed in a hierarchical way. Like, there was there were initially some stars. Initially, there was just, just plasma. They formed like, hydrogen and helium and so on. From there came first stars, and the first stars exploded and formed a black hole. And many of these black holes finally coalesced and then formed the supermassive black holes. And that's how it just grew over time. And then right now, we cannot escape our gravitational potential that very easily. So we will stay bound for at least foreseeable future, I think.
Right. And this is a question from classmate Pushpa only. I mean, I think you did indicate about this when you spoke about redshift. So the question that she's asking is, on what basis do we identify the old, medium-aged, and then the new-age galaxies? I mean, how is that done is what she would like to know.
Yes. So it is because, it is just the concept of redshift. So what we are saying is like, something that is receding from us, the wavelength is increasing. So which means it is with the same coin, we are talking about the cosmic microwave background as well. Because what was emitted at that 0th instant is like so far away, and it's moving so further away that whatever emission that is emitted is moved into microwave frequencies. So just by studying galaxies at different wavelengths, if you study a galaxy at infrared wavelengths, then you're talking about much older galaxy. So it is just this wavelength is what has the clue about the age of the galaxy as well.
So, Ramesh, for the sake of time, I think we're already at the top of the hour. So for the sake of time, I'm going to directly jump into one question that everybody wanted to ask is, so if I have my child comes up and says that I want to pursue astrophysics, it's very interesting for me. And if they are at the stage at which they want to make a decision, I'm presuming most of them have finished school or probably they're doing undergraduate in some form. And if they want to pursue that in masters, so what are the career prospects that one gets in the pursuance of this interest in astrophysics?
So I think there are two answers. One thing is like, career prospects. You can, yeah. Do you want a short answer or a long answer?
No, I think an answer that will convince all of us.
Okay. So, so I did put one of those things. So basically, to get into this field, a PhD is more or less, the very prerequisite. And to get a PhD, the other prerequisite is to have a bachelor's and, or a BSc, MSc combo and a good grounding in math and GR and QM, because, modern students need to have these grounding in these theories. And as usual, a curious mind, I think. And then other, unwritten rules are that, you need to have a good thesis, possibly a research article, and research experience in terms of internships and trainings and research institutes, good programming skills, and these days data science skills. And then, and also you need to research the department before you are applying, try informal emails, and, and best is, and don't ever send generic emails is one thing, because I do see PhD students and this is what happens. People just send a sharp-null email to all, and that really doesn't work. But here are career things like so during PhD, it really depends on location where you're doing. Like, it can be project-based as in Europe. It can be coursework-based as in the US. And, somebody asked, like, is there room for individual thinking and visualization? I think ample room, because, visualization is, imagination. You need to have the power to imagine, but, within boundaries. You cannot imagine something like, people do appreciate how they say multidisciplinary work, but you cannot combine psychology and astronomy. They are just they are orthogonal fields. So something of that sort. So, within boundaries, it will work. Like, you can use techniques that are developed for identifying cells to identifying galaxy structure, for instance. So such things are possible. So which means there's room for individual thinking. And then again, you need to also continually assess, because sometimes you do start a PhD out of good research, but at the end you need to be practical as well. Would you have a permanent job? Can you make a career out of it? And then therefore, I think you should also have an exit plan as well. So after PhD, what are the career prospects? I think the first thing that people normally do is something called postdoctoral research. So that's where you go, wherever you do PhD, you cannot stay there. You have to move because that's the way the field is. And then you need to go gain additional research experience elsewhere. So all of these are paid, of course. PhD is also a paid thing, where it was paid at a minimal level, but it is enough for you to survive. So I think if you're looking to money, this is not the place. That I'd like to say at the outset. So, but after PhDs, you do your postdoctoral research, and then you can start applying for, a postdoctoral research can be 1 or 2 postdoctoral researchers. They can be 2-year term, 3-year term, 5-year term at the maximum. So you do a couple of postdoctoral research stints, and then you start applying for something like teaching positions where you become university professors, or you can apply for research positions as in staff scientists, as I do, or you can do technical positions like, where people build satellites, or where people build signal processing equipment or antenna, and so on and so forth. So I think this is kind of really a hand-wavy answer to your career prospects. But if you have any pointed questions, feel free to just email me or message me, and then I can fill you in with much more details.
That would be very useful, Ramesh, because see what you have said in essence is this is not a quick money-making job.
Yes.
This requires you to have long-standing commitment, extraordinary amount of keenness to sit down and do and study and invest on yourself and to the field. So it's going to take some time. It needs deliberate effort. And
Yes.
that is not like finishing your degree and getting a job in any of the programming companies or become a software developer or a mechanical engineer in a company. It's not that easy. It's not a plug and play role. You evolve into who you want to become over a period of time. So
yes, I'd agree to that assessment.
right. So since the time is up, Ramesh, so I want to ask you the last question that I personally wanted you to answer. There are a lot of questions which are there in the forum. So post this, we will open up people to open up and ask you questions directly as well. So you could also see what questions are there, Ramesh. So the question that I wanted to ask you, Ramesh, is now this is such an interesting field because the more you look up the sky right now, you know that you don't know anything. So, and you also get a feeling that you're such a tiny speck when it comes to what is happening at the largest universe level, right? So,
Yeah.
it's so big. So, tomorrow or even tonight, if we step out and we look at the sky, what is one thing that you would want to think when you look at the sky?
Just give me a second. I'll just stop the share and then I will get another. I'll just show you. So, do you see this this image now? Okay, so this one, kind of, this is called the family portrait. It's, one of an US astronomer called Carl Sagan. He asked, he kind of requested, of course, with lots of support from other scientists, when Voyager was, I think this was close to Pluto. So so this is kind of the family portrait. So he requested that we make a picture of the solar system, and this was made from the orbit of Pluto. So when in the orbit of Pluto, when Voyager turned around and made this picture, the Earth looked like this tiny speck, as you see over here, this tiny dot where the mouse is. Now this is the kind of thing that we are dealing with. The astronomy in the end brings us something like a humbleness in ourselves, telling that the universe and everything is so big that we are really a tiny speck. The Earth is a speck over here, and in this speck we are tiny grains and tiny atoms with our own egos, our own wishes, our own fights, and everything else. So I think that kind of, I would just just ask people to contemplate on that basically.
Thank you so much, Ramesh. And there are some interesting questions which are there in the chat, so which we would open up after the session if you have time. So please spend some time with the participants. Please answer some of those questions. So some of them you've already answered while you presented itself. They did come at a later point of time when we were presenting, but some of them are hypothetical. Some of them are very philosophical. So it's going to be an interesting conversation you would like to have. So let me hand it over now to Sam. So
James.
with that, I thank you very much. I really enjoyed Ramesh. What it has done to me is that it tells me that you know nothing. So probably we need to go back and study. So do some research, and if there is some material that we need to refer to in terms of videos or anything that's interesting for us, sit down and watch. Where should we access those? Just let us know that.
Okay, no, I think these days it's just a Google click away. I would say, just I think the trick is in formulating the right question. So I think you can get you can get a lot of shit back from the internet, but I think you'll have to formulate and filter out the right material from there.
So with that, Ramesh, thank you very much. I enjoyed talking to you. So over to you, Sampath. Sam, are you there?
Yeah. Thank you, Balaji. And so on the offset on this August day of launching TED K'96, It was absolutely a pleasure and joy to have you, Ramesh. Come and open up this TED session in Kitwood and to share such wealth of knowledge and especially your journey for the past 30 plus years and how you have gone from one show to the other to where you are, peeping through the galaxy and, counting the stars. It's so very amazing. So first of all, as Balaji mentioned, I was so humbled with our forefathers telling us in Tamil, "Katrathu kaiyalavu, kalladado ulagalavu." So really humbled to start there. And this is a thank you note. So I'll just shelf off all the awe and wonder that I had with your disclosure and really focus on you, sir, to thank you for a wonderful session that you have delivered. And with the yearbook that James had put together, James and team had put together, and to see your wonderful journey from Karunya to IIT Madras and from there to Raman Research, taking a cue there in your heart to go to Amsterdam and to continue your research and your fellowship there. One thing that strings in my heart is you are intuitive and you respond to that intuition in your heart to take a step, to take a leap, to pursue that dream that is in your heart. And that is one of the biggest takeaways that I had when reading through your write-up in the yearbook. And then to see the heights that you have reached, that really also humbles us, Ramesh. When I met you during Relive, when we had the conversation for a couple of hours, you, me, and Veera Nagendran, and then spent a whole day in the retreat center, I didn't know that you had reached astronomical heights in your career, but in the ஒரு வால் நட்சத்திரத்தை போல நீள்கின்ற உன் பட்டங்களும் பதவிகளிலும் முதலில் வகிப்பது நீ ஒரு நல்ல நண்பன். You are a great friend. தன்மை மாறாத ஒரு நண்பன். So that should be your first degree. And followed அப்படி ஒரு தன்மை மாறாத நற்குணம் படைத்தவனுக்கு இவ்வளவு பட்டங்களும் பதவிகளும் தொடரும் என்பதில் எந்த விதமான ஐயமும் இல்லை. So to start there and to see your wonderful journey, even as our children are watching you today, they should also know it is not all about books and marks, but also about your character and your steadfastness in loving humanity, and to see that, nothing affects the person that you are, and to continue this journey with one thing that is centered in your heart, which I believe you're humble not to express, is you want to do something good for humanity and to bring some goodness into the lives of people. And I'm sure, Ramesh, in the days to come, the findings that you are, pursuing will one day reflect in the textbooks that our children and our children's children will read. And you will join the long galaxy of our forefathers, Aryabhatta, Bhaskara, and your name will be there in the Hall of Fame in our country. And you've made us not only us proud, but also this country proud in your journey. Continue your journey. We are the galaxy of your friends. We will always be there for you. We will encourage you. We will strengthen you. And you can reach out to us as much as we can reach out to you. And we are in this journey together, sir. Go forward, reach the skies. We are there to salute and applaud your achievements one after the other. May this be a journey that we do something good for humanity in this small time that we live here on earth, and leave back a legacy that will be a blessing for generations to come. So thank you so much, Ramesh. As a traveler, I have only one question to ask you. How எவ்வளவு சாத்தியமா இருக்கு ஸ்பேஸ் டிராவல்? நான் பூமியை சுத்தி வரேன், கேலக்சியும் சுத்த முடியுமா அப்படின்றது தான். பட் அந்த கொஸ்டினுக்கு ஆன்சரை நான் தனியா உங்ககிட்ட சாட்ல இருந்து நான் வாங்கிக்கிறேன். There are many who are with questions pertaining to today's disclosure. So we will get into that. Thank you once again, Ramesh, for a wonderful presentation and making our hearts really rich with wisdom and knowledge from you. Thank you. Thank you so much.
Thank you, Sampath. You raised my bar, so hope to live to that expectations. Thank you again.
Doubts, Ramesh. The only one thought that I wanted to say and close is, I don't think it will be right and just if we do not thank each and every one of you who had taken this time out on a Saturday evening to be part of this. And this is the best support that you can ever show. Thank you so much. I think, James, how many people did we have sign up who have logged in today, James? I mean, do you have a count?
Yeah, we had 32 at one point. Now we have 25.
Right. So, I mean, 32 is a good participation. That's great. Now, being the first session, please feel free to comment and give us your feedback so that we can improve on this a little bit better, so that it makes more enjoyable to you. And just to prelude, we have already identified the next speaker. So we will probably do the next TED K'96 session. And the next speaker is going to be a lady. The next speaker is going to be a lady. We've already identified. So we will come back with more details on the next TED speaker. Thank you very much from my end. And James, now starting from now on, now we can unmute everybody and we'll open for questions that people might have for Ramesh.
I'll stop recording also. Yeah.
Hey, that can be continue. Recording can continue, man.
No, formally we close the session, Siva.
Okay. Before you close,
Okay,
Balaji, so
okay.
let me also join you in thanking everyone, right? So
Yes.
I think, as I said, this is a Saturday time to spend with your family or even to grab your dinner, but you are here listening to me. So I think that is really telling something about the support that you guys have, and this is what I was all the way worried that I'll have to I'll have to do justice to your time, and I hope it did. So if I do not completely hit the mark, I would have at least tangentially touched the mark, I think.
No, I think it was done very well, Ramesh. I mean,
Yes, excellent, man.
And we also
we are privileged to be here, Ramesh. It was excellent presentation, very knowledgeable. Thank you very much for that.
Thank you, Anand.
Right, yeah.
So now we will have more speakers who would be enthused and motivated to come forward. Like, for example, we know Danny has been in the trucking business for all his life. He'll come and give us more insights about trucks, Danny.
Hey,